networks that are too deep or too shallow, what we found is that the network loses the compass when it comes to the computation of the gradient. And then sometimes it shows that, as if the network has converged, but when you look at the solution, it can become actually a trivial solution. And there is more and more, there are papers that talk about why pins fail, why pins might not work at sometimes, and different people attribute it to different factors, and there are different ways to handle that. But at least by that time, we got some confidence, we got some understanding of what and how and why things converge, and what also we should be avoiding, and what are the things that we should be checking for while we are developing this technology. The next question that we started addressing is, can we predict with a single network? So the idea at the time was to use, instead of training for each time step, is I want a single network that can understand what happens over the time. And then at the time, there were some options like the LSTMs, like the GRUs, and also that the exciting thing that we were thinking about at the time was the temporal convolutional network, and we really liked how the idea of the 1D convolution of time and how it ciphers the information across times and allows us to get a network that learns from the past, not from the future. And we don't have the time to go into the details of the temporal convolutional network. So we started developing the PyTCN, the physics-informed TCN. So again, we started with doing that for the non-local damage problem. And this is one of the examples that we showed. So we got very decent accuracy. And then we started seeing some interesting things in terms of the computational behavior here. So here I'm plotting the time in second for each increment in terms of the loading increments in the model. And as you can see here, the dark blue is the monolithic finite element. And that time increases exponentially as you continue the loading, and as the crack is getting longer and wider, that increases exponentially. When you switch to a staggered finite element scheme, there is still a rise, but at a lower rate. But the even more interesting one is when we switch to I-FENN, although we have some bumps here due to changing the loading step size, but it remains pretty much constant. Because the network is there and the network has an idea about the final solution, then it kind of regulates that computational cost. So even though you're getting to much more complicated regimes in terms of the response, at the end of the day, you still get the same cost in terms of the time per increment. And now I'll switch, so the PyTCN was originally developed for the thermal elasticity problem, but for the flow here, I explained the non-local damage first. So we developed this PyTCN for the thermoelasticity problem. Again, you have two equations, the balance of momentum. Here we're solving for the temperature using the network, and for the displacement using the finite element setup. We did try that on several examples, and in all of them, we're getting very good accuracy, and we're also getting a good scalability. So the larger the model, the better performance is the neural network. I'm going to talk more about that in a bit. But as we're looking into this, we realize that doing physics-informed models, especially when you go to 3D and then with the thermoelasticity, we have to apply real boundary conditions. It becomes very complicated. So we're thinking about reducing that to a variational form. We're using a sort of a weak form setup. So in this case, with the variational TCN, the network is learned to respect the variational form, which is one lower order. So it's a first order only in terms of the derivative. We're hoping that this will simplify the computational effort. In one way, it did. On the other hand, we realized also that we're not enforcing the physics as strongly as the physics-informed setup. So we had some trouble with respecting causality and making sure that the results make sense at the end of the day. That being said, we still got decent results, and these were all milestones along the way. And this is one of my favorite plots to show, because it shows how with every change that we make in the model, we are actually doing better. So the finite element model here, this is the blue line that you see. And then you have the red line, which was uh, our first pass, which is training the PyTCN with the strong form and the automatic differentiation. And then we went to the green, which is the variation form and the automatic differentiation. And then we said, okay, let's get rid of the automatic differentiation because it doesn't work really well for larger problems and more complex derivatives. Let's replace that by finite element shape functions. And then we get the VFSF, the variational form and shape functions. And this gives us the orange line. And then you have the purple, which is the data-driven, which we're only doing it for benchmarking. We're not really interested in the data-driven because it's limited extrapolation ability. But what I want to show here is that with every improvement that we do in the model, we're becoming more and more competitive with finite element, and we are becoming even more efficient as the model scalability, as the model scale increases. So where do we stand right now in the flow? So we kind of understand where the savings come from. We also understand whether pins can be realized as a numerical method, and we are familiar with what we should be and what we shouldn't be doing. And we also answered the question about can we predict with a single network. Now we look at other generalizations. So can I-FENN handle multiple unseen loads? Can I-FENN handle different geometries, boundary conditions, models, configurations? Can we implement I-FENN on an HPC platform? So everything that I've shown up to this point was really done using either a MATLAB code or in Phoenix, which with either you can implement on HPC, but what I mean here by implementing on HPC is to use a really massively parallel package to push things to the extreme, which we are looking for in terms of like full-scale geomechanical simulation. So to address the first question, this is where we start. I mean, I'm talking here about question 4A, and this is the work of Fuad, who's here with us on the call. So we have introduced I-FENN for thermoelasticity using the DeepNet. So in this case, we are resulting to the DeepNet technology, the deep operator neural network. So we are, instead of the mapping the input to the output, we are mapping now the input space to the physical space where we are expecting to see the results and mapping the function from here to there. So this takes the load and the strain history as the input, and then the output is measured at the X, Y, Z locations. And here we are looking to predict the T or the theta, the temperature at the end of the day. And then we started moving from using Phoenix and MATLAB, in this case, to an implementation within Deal2, which now upgraded our, our actual performance in terms of what we were seeing, and allowed us to go to larger problems, more complex problem with the Deal2 solver. And then Fuad used that, and we started playing with different configurations of the load, either variable body loads and then also variable surface fluxes. And for the first time, I'm training on a range of loads, and then the network, when we are testing, we're testing on something that the network has not seen at all. So it's a load setup still within the range of what it has been trained on, but that specific load scenario the network has not seen before. So that gives us an edge in terms of the generalizations that we were looking for. So we did that. We got pretty decent results in terms of the accuracy. We did the same thing. I'm not going to go through all of the details here, but let me go to that, which has enough of the details. We did the same thing for poroelasticity. So in this case, we are predicting the displacement using finite element. We're predicting the fluid pressure using the neural network. And this is an application to an excavation problem. Again, I-FENN behaves overall very well. The errors are very small. We see, some higher errors in the cases where the temperature, this is the type where this should be the pressure, where the pressure is close to zero. So overall, the accuracy of what we are seeing is very well. But we also then use this to start looking at the scalability again. And we're starting doing these problems with more and more, with larger number of elements and so on. And the best thing that I look at in this graph is not really the absolute values that you see on the right or left-hand side. What I'm interested in is the slope, that as my problem becomes more complex, as I need more and more elements into the problem, the savings actually increase, which tells me that I-FENN has the promise to shine more and more as the problem complexity increases, which is understandable from the computational cost point of view. And then this is to the last part of my talk today. This is our latest paper on the topic. So we started moving to phase field fracture, and here we wanted to push this more to do further generalization. So in this case, the finite element model is again used to solve for the displacements. The phase field, however, is being solved for using a neural network. So the neural network is learning how to map H. H is the strain energy density, which drives the phase field fracture growth. So the network learns how to map the H to the D, the damage variable. And unlike what we have done before, we have not used deponets, we have not used pins at a single snapshot. We said we want to try the CNNs, the convolutional neural networks, physics-informed convolutional neural networks, and we were hoping that these are going to give us the spatial mapping and respect the spatial relationships that we are looking for in this work. Now, the interesting thing here is that we started training the network and we started pushing more and more to make the network as small as possible and give it as little training as possible. Before I get back to that, I want to look a little bit. So, as I said, we're training only with a limited set of increments as light as possible, and that showed us the generalization, which I'm going to talk about. What I want to mention here is what we have done to the CNN. So we did not take the CNNs as they are. We started making some changes in order to make them respect the constitutive relationships that we are looking for. So one of the major things that we have done is to introduce the symmetry in both directions to enforce the symmetry in terms of the translation and rotation. So we applied that to the kernel to make sure that we respect the phenomena that we're trying to model. We also, in this case, we replaced the autograd or whatever automatic differentiation by a finite difference approach for computing the derivatives, particularly the Laplacian in this case. And here is a snapshot of the results. So we take a single notch tension problem and then the load is vertically applied. I hope the screen is showing you these contours evolving fast enough. But there is an excellent agreement between the finite element and the I-FENN, and to give it that without the video. So you see here that there is a very good match. This is a very unstable problem. So, within a very small increment here in the displacement, you can see some difference between the crack length here and the crack length there. But overall, the reaction forces are in a very much agreement. Not only that, we use the model to compute the energies. So the elastic energy, the fracture dissipated energy, the total energy in the system, and there is an excellent agreement between the finite element and the I-FENN. Now, as I said before, as mentioned here, this network was only trained on 2 H+ profiles. So it's a very small network that trains in less than 5 minutes, and then the training was only done here using the S&T problem on 2 increments that the network was asked to train on. However, we started using that trained network to model more complex problems that the network has never seen before. So we try 2 different things, the double notch tension and the asymmetric double notch tension. So in the DNT, we add another crack on the opposite side. We don't train the network anymore. We just take the trained network, we plug it into the I-FENN setup and give the finite element part of the I-FENN the new geometry, the new cracks. Without further training, we're getting an excellent agreement. Again, for the ADNT, we rotate the cracks, we've set them a distance apart. We start the model, the network has not seen these cracks before, and we get an excellent agreement as well. And this is so far between using the deep nets in I-FENN and using the physics-informed CNNs in I-FENN. this is as far as we have been pushing in terms of the expansion. So we did address these problems, these questions that we have just asked, and now we are at another checkpoint. We now want to really expand this to large scale applications. So in order to do this, we are working on improving our capability and what's out there in terms of the physics and form networks. We're also looking at resolution independent approaches, because as we are scaling up, these are going to mitigate many of the problems that are prohibiting our work right now. We are looking at extending this work to multiple coupled physics. So instead of doing only polar elasticity or thermoelasticity or fracture, we're trying to combine these effects. So for example, one of our projects that will start very soon is to start polar thermoelasticity and try to model that with I-FENN. We're collaborating with colleagues at Lawrence Livermore National Lab and embedding this now into the GSX platform. So to summarize, what we are presenting here is an approach to combine the best effects, the best of both worlds in terms of the finite elements and the neural networks, get the best of both worlds in terms of the rigor, flexibility, efficiency, data-driven learning, and trying to mitigate the extreme time demands, memory demands, and also to avoid the issues related to reliability and their interpretability in the neural network. It's a continuous journey, and we are looking ahead, very excited to continue looking always for collaborators and looking for ideas to continue enhancing this work. I'd like to thank the Shore Center, Sand Hazards Opportunities for Resilience, Energy, and Sustainability, for partially funding some of this work. Their funding is very much thanked and appreciated for that. And that's the end of my talk. Our papers are out there. In all of our papers on I-FENN, the code has been shared with all of the underlying data. So feel free to give it a try and start playing with it, and let us know what you think.